Hi, in this video we're going to review atomic structure, molecules, and isotopes. We can begin with ancient history. In the ancient Greeks, there were two philosophers who argued about what made up matter. There were two camps. The atomists were led by Democritus in the lower right-hand corner there, and they thought that everything was made of atoms. They thought there were individual particles of everything. On the other hand, the guy in the statue in the upper left, Aristotle, thought everything was a mixture of air, earth, fire, and water. He had a more simple idea of the elements. And as they argued, Democritus said to him, everything's made of atoms. And Aristotle said, well, what's between the atoms? If there's these little particles, what's between one and the other? And Democritus had to say nothing. There's nothing between them. They're the smallest things. And Aristotle said, well, nature abhors or hates a vacuum. It can't be. And that sounded right from a philosophical argument about nature thousands of years ago. And Aristotle's argument sounded better, and his idea of atoms or elements stuck around until the Middle Ages, when other experiments showed evidence that atoms are what nature is composed of. The word atom comes from the Greek word for indivisible. The prefix a can often mean something is not, as in words like apolitical, atypical, or asymmetrical. Of course, the prefix can mean other things too. You have to know the context. Words like atop, afar, and alike don't mean that something is not on the top or not far or not like. And then the root word tome from the Greek tomos means to cut, and we see it in words like appendectomy, mastectomy, or gastrostomy. Together, a and tome mean that something is not cuttable. So we can see how the words are made up. This diagram shows for humans, these are the elements that compose the human body. The elements are the different kinds of atoms, and we can use the memory device, the made-up word chon, C-H-O-N. It's not a real word, but it helps us remember carbon, hydrogen, oxygen, and nitrogen are the elements that make up most living things, including humans. Now, you can find different studies on this, but if you went to a chemist and said, give me, a certain amount of pure oxygen, pure carbon, and pure chemical nitrogen and such and so on, it's only about $4.50 worth of chemicals. However, what our body does with things, when we combine them into a greater whole, we can have organs in our heart or livers or kidneys can be valued at thousands of dollars. So it can help us realize we are looking at tiny little particles, but don't forget the bigger picture. Do these elements and atoms make you who you are? Show me an atom of dreams or passions or sorrow within you. On the other hand, you could say, well, when we build molecules of hormones, serotonin can make us feel happier. So there is some relationship between chemicals and our emotions, but it's still a tricky thing, and that's stuff you have to navigate as you make up your mind about how life works and what it means to be alive. You'll also notice here that there are trace elements, things that are in our body in very, very small amounts. Things like iodine, which are still important. For example, your thyroid glands need iodine. And without them, you'll have a thing called a goiter, a swollen thyroid gland. So there are major elements that make up the human body, lesser elements, and just trace elements that are present in small but still important amounts. A guy named Dalton, who lived in the Manchester part of England, helped put all the ideas of atoms together into what's called atomic theory. This happened much, much later than the ancient Greeks, but it still helps us realize some key points about how we make sense of the chemistry of living things. All elements are made of atoms, so there's different elements, and each kind of element has its own kind of atoms. Atoms of the same element are identical, relatively. So if you have an element like carbon, all the carbon in the universe, as we understand it, has the same number of protons. There's things in common within the atoms of one element. And then atoms of different elements are different in the number of protons they have. Then atoms of different elements combine in whole number ratios to form what we call chemical compounds. So for water, there's 2 hydrogen for every 1 oxygen. It's 2 to 1. There's no such thing as 2.5 hydrogen for every 1 oxygen. They're whole number ratios. And then chemical reactions occur when atoms separate, join, and rearrange the atoms in different chemical compounds. In chemistry, the atoms themselves are never really changed, just moved around. If we talk about nuclear physics, on the other hand, well, that's a separate thing, and nuclear reactions can change atoms themselves. A guy named Thomson discovered a part of the atom called electrons. He used a thing called a cathode ray tube, and there's a beam of electrons glowing green in this tube, and they're moving from one side to the other, and then by applying magnets to them, as we see here, the electrons moved away from the negatively charged part of the magnet. Magnets have positive and negative parts. Electrons are moving away from the negative part of the magnet. Therefore, this shows that electrons have a small size but a large charge. And so from math based on the strength of the magnet and how the electrons were moving around, they figured out the size of them as very tiny and an electrically negative charge. Now, atoms themselves are electrically neutral for the most part. So there had to be a positive charge to balance out those negative electrons. With time, they would be discovered as protons. Another big discovery in what makes atoms was an experiment by a guy named Rutherford, and that showed that there is a nucleus to atoms. What he did was take a thin piece of gold foil, and he shot a kind of radiation called alpha particles at that gold foil. Now, he knew that there were electrons, but he didn't know where the protons were at. He thought the radiation would just go straight through the foil, but with a detector around the foil, he found that the alpha particles were bouncing off of parts of the atom somewhere. And so, using this screen to detect the scattered alpha particles, he could see, because of his experiment, there must be a dense region of protons within the atom that the alpha particles of radiation were bouncing off of. And so that's where we got the idea that atoms have a nucleus, this experiment. Now we can ask, how small is an atom? They're so small individually, a photon of light could miss it. To give us a sense, in a 1 centimeter long groove, there's 50 million atoms fitting in there. We have a thing called scanning electron microscopes that can actually view the surface of atoms, but here, the head of an ant is millions of atoms wide. A grain of pollen is many thousands of atoms wide. And here, an image from a scanning electron microscope shows us some individual gold atoms. So we can kind of see them, but we still don't fully understand them. We have a lot of good ideas about them, but the physics that work for atoms is different than the kind of physics we use when we think about the friction in a car or throwing a football, or the physics works differently at that microscopic level. Now then, There's a lot of important vocabulary words on this slide. The nucleus is the center of an atom. It contains protons that have a positive charge and neutrons that have a neutral charge or no electrical charge. For any one atom, we can talk about its atomic mass, which is the sum total of the number of protons plus the number of neutrons. Remember, every different element has a unique number of protons. The number of protons in a hydrogen atom is going to be different from the number of protons in a helium atom, for example. Then, outside of the nucleus, we have what are called electron shells, or also called orbitals. Electrons have a negative charge. They are so small that their mass or weight is negligible for what we're talking about here. For any atom, the number of electrons is going to be equal for the number of protons at the beginning. That can change, which will give us a thing called ions. But at this level, at this starting point, the number of electrons is going to be equal to the number of protons. The negative ones and the positive ones balance out for a neutral atom. The electrons that reside in shells or orbitals farther away from the nucleus have a higher amount of potential energy within them. Their location and how they move imbues them with more energy. An atom can have a number of shells, but the farthest or outermost shell is called the valence shell. And the electrons within that shell are the valence electrons. These are the electrons of an atom that interact with other atoms, and they determine the chemical behavior of that atom. Will it be an ion? Will it want to bond with certain things or not other things? We have a way to talk about how atoms interact called the octet rule. Generally, atoms react to obtain a stable number of 8 valence electrons. We'll talk more about that in another slide. So here we see a small little table to help us see the symbols for electrons, protons, and neutrons. You have a lowercase e with a little negative superscript to remind us that electrons are negatively charged. And then we have a little p with a positive superscript to remind us that protons are positively charged. Now, atoms are like planets. Here you see some diagrams of different elements and the example atoms of those elements. You'll notice there are a number of different energy shells or orbitals where the electrons reside. Now, the first orbital or energy shell only has room for 2 electrons. And after that's full of electrons, the next set begins filling in the next shell, which has room for 8. Likewise, in the third shell, there is room for 8 more. It gets a little bit more complicated going forward, but that's what we have at this level. So oxygen has 8 protons. Its atomic number on the periodic table is 8. Every oxygen atom in the known universe will have 8 protons. It'll also have 8 electrons to balance those out, although that can change because ions exist, but that's for a later lecture. But there are 8 protons and then 8 electrons. The first 2 go in the first energy shell, and then the other 6, there's 8 altogether. 2 plus 6 is 8 altogether. They go in the valence shell, or the shell that is farther away. And so on for other elements. Sodium has 11 protons, which means it has 11 electrons to pack into orbitals. The first 2 go in the first orbital. The next 8 go in the next one, and then that's full. So that's 10 altogether. 2 and 8 is 10. But it has 11, so we have to break in to a third energy shell. Remember, the periodic table is organized by increasing atomic number, and the octet rule tells us that atoms react with each other in a way that tries to get them to have a stable or full valence shell. That means 2 in the first ring and 8 in the additional outer rings, or the valence shells, the farthest away shells where the electrons reside. Trying to put the right number of electrons in each shell is why atoms react. Now here we have the periodic table of elements. I know a lot of the details on this one are too small to see, but this is giving us the big picture. The periodic table is organized by increasing atomic number. In the upper left, it starts with number 1, which is hydrogen, moves up to 2, which is helium, and so on. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then we start another period: sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, and so on. It is organized by increasing atomic number, which is a symbol for the number of protons in an example atom of that element. Then we have other groupings. This little yellow diagonal group are called the metalloids, and it divides the periodic table into metals on the left and non-metals on the right. Most of the elements of living things are non-metals. Carbon, hydrogen, oxygen, nitrogen are all non-metals. You might notice hydrogen's on the metallic side, but it's still a non-metal. The thing about hydrogen is it's so small, it gets its own special groupings for lots of things. Then we call the up and down parts of the periodic table groups. For example, the noble gases is a group on the far right, and left to right we have periods. The periods reflect filling in energy levels for electrons. The first period, very small, with just hydrogen and helium in it. The second period, with 8 elements in it, reflects the 8 electrons that can exist in the valence shell of the elements. At the end of the period, we have elements that have full orbitals of electrons, which makes them chemically happy. They've met the octet rule. That means this last group, the noble gases, is very unreactive because they have the exact number of electrons in each atom that it requires. So if we zoom in, you'll see symbols for the different elements in the periodic table. You'll see an atomic number. That's a whole number that indicates the number of protons in that element. So every carbon has 6 protons. Then we have the name of the element in the periodic table and the thing called atomic mass. I'm going to read it to you here, but we're going to come back to it near the end of the lecture so you understand. The atomic mass is a weighted average of the masses of all the elements' isotopes. We'll talk about isotopes in a bit. Rounding the atomic mass to the nearest whole number yields the mass number of the most common isotope. That won't make sense till we talk about isotopes, but hang in there. And so there's an atomic number, but then there's a mass number. Now remember, an atom is neutral, and given the periodic table and the name of an element, you can figure out how many protons are in it using the atomic number. For a neutral atom, the overall net charge, the positive charge plus the negative charge, will give us 0. So the number of protons will equal the number of electrons. So we use the periodic table, and that tells us the number of protons. We use that to find the number of electrons if we need to. Again, we're going to have to come back to isotopes in a little bit. To revisit the octet rule, noble gases are stable because they have just the right number of valence electrons. That's 2 for helium and 8 for the rest of the noble gases. They are balanced energetically. Other elements react to gain or lose electrons to reach 8 valence electrons, although the smaller ones just try to have 2. So here we see some different atoms, and we can see unstable or more reactive atoms. For example, hydrogen has 1 proton and 1 electron. It's trying to fill the octet rule, meaning it's trying to get 2. Remember, for most of them it'll be 8, but for hydrogen and helium they're smaller, so they just need 2 electrons. So here helium is much more stable because it's fulfilled in its orbital of electrons, and it has 2, which is all it needs. 3, it would have 1 too many. 1, it doesn't have enough. Carbon is atomic number 6, meaning there are 6 protons. And for a neutral carbon atom, that means there are 6 electrons. The first 2 of those 6 go in the inner orbital. Then the other 4, leading to 6 altogether, 2 plus 4 is 6, go in the outer orbital. Carbon is reactive because it wants to get 4 more valence electrons, which would give it 8 valence electrons. So neon has an orbital that's filled up. Neon is atomic number 10. It has 10 protons, and so protons and electrons are equal, and so in the orbitals we can count out the first 2 go in the inner orbital, the other 8 go in the valence or outer orbital, and so that gives it 10 electrons. And so on with sodium or argon. Sodium with atomic number 11 has 11 protons and 11 electrons. It has 1 extra that it doesn't want because that is not filling the octet rule. We can show these as what are called atomic symbols, or you could also call these nuclide symbols. They show the mass number and the atomic number for different specific atoms. So for this particular sodium atom, the atomic number is 11. That tells us 11 protons. The mass number is the protons plus the neutrons. So 11 plus 12 tells us that in this atom of sodium, there are 11 protons and 12 neutrons. The number of neutrons can change, as we'll see soon. So this particular sodium could be called sodium 23. It's one kind of sodium, or one isotope of sodium. Remember, for all the sodium that we know of, the atomic number, or the number of protons, will always be 11. That won't change. So isotopes are atoms of the same element with the same number of protons, but different numbers of neutrons. The number of neutrons changes. This leads to the atoms of the same element having different mass numbers. Chemically, they react the same, but we can tell that there's a difference. So, for chlorine, there are different isotopes of chlorine. Chlorine has the atomic number of 17. That'll always be the same for chlorine. But this chlorine has 18 neutrons. This one has 20 neutrons because 17 plus 20, that's protons plus neutrons, gives us 37. These are the mass numbers of 2 different chlorine atoms. So they're 2 different kinds of chlorine. They both react in chemically the same ways. They would both be in salt, for example, because salt has chlorine in it, but they are detectably different because they are isotopes. There are radioisotopes. Again, isotopes show the same chemical behavior, but they can differ in ways that we physically detect them. Radioisotopes are unstable. They can decay because of radioactivity, and we can use that to trace their behavior through the world. So, we have learned a little bit about atoms, subatomic particles, the periodic table, and isotopes. We'll use these ideas to build on in future lectures. Thanks for watching. Bye.